Okay, hello once more, continuing our sinusoidal current and mathematical approach, how to deal with it. Last time we discussed the basic principles, how we are using in mathematical model resistors, coil, and capacitors. The main idea that all transformation of electrical energy into any other type of energy, mechanical, chemical, heating, light, and so on, it will be modeled as a resistor, as a consumer, and all electromagnetic energy that stays inside our system without consumption, just circling inside our system from one element to other element, and so on and so on. It will be modeled as coils and capacitors, as energy storage elements. Coils, they are dealing with magnetic field. Capacitors, they are dealing with electrical field. That is how our mathematical model deals with consumption and electromagnetic energy inside system as electromagnetic field. Also, we discussed that we have basic equations to deal with them. It was just ordinary Ohm law for resistor, that voltage equals current multiplied resistivity, and differential equations for resistor, for coil and capacitor. For any coil, we discussed that voltage should be derivative for current. If we speak in terms of constant inductance, the characteristic how strong magnetic field will appear near this coil. If our element is linear, if magnetic permeability of this object is linear, we could describe its characteristic as a constant, some constant, and it will be inductance L in Henry. And also for capacitor, we have derivative from voltage. Also, if we're speaking about linear element, as capacitance will be constant, how much charge could this capacitor storage and how much amount of energy will be inside this capacitor, how strong electric field will be inside this capacitor, it could be modeled as capacitance. And because we are continuing discussing only linear tasks for now, then RLC will be constants, R in ohms, L in Henry, C in farads. Our main equations for resistor, coil, and capacitor. Also, sometimes you could see pointing for resistors like that, especially in some mathematical programs as Simulink or Electronic Workbench and so on. It is the same pointing, it is the same element. Just in Ukrainian speaking literature, generally it's pointed as like this, at this element. Then, that is why all our calculation that will be on alternating current, any type of alternating current, should use this equation. And we are start to solve differential equation, at least in derivative of time. And sometimes it could be also a partial derivative of time and space, some space coordinate in one-dimensional, two-dimensional, or three-dimensional coordinate system. Then all alternating current will be in differential equations, and then the main questions, which type of alternating current we are using and how we could simplify these equations, because generally it is not very comfortable to deal with them. And in all situations that we could simplify this approach, it should be simplified. That is why generally alternating current could be periodical and non-periodical. It is mean that with some repeatance of signal, it could be a sinusoidal current, or it could be any type of periodical current. Just the main idea that should be some repeatance. And non-periodical, any type of non-periodical function without extremums or with some extremums, but some not repeatable process. Then it depending which type of alternating current, that is mean how mathematically we will solve it. For now, we are starting from the most common case in electrical engineering, because we generate and transports and consume electricity using sinusoidal current, or try to use sinusoid. If we obtain non-sinusoidal, it is just because of some disturbances, and we try to neglect these disturbances and make our signal as much sinusoidal as it possible. That is why generally the most common case is sinusoidal. That is why today we will discuss what mathematical approach we will use for differential equation to simplify them into the sinusoidal case. Generally, we have situation like this. If it is alternating current, we have some time function with quite complex equation for solving. That is mean we have some derivatives, we have some system of equation, and not very obviously how to solve them. There is quite useful mathematical thing to use such called operational equations to represent some time function as other type of function from the other parameter. Not time, but some other parameter. And if system of parametrical equation will be much simpler than system of time equations, that is the main goal why we are doing it. If we obtain more simple system, then it will be better for us for obtain the answer. Then after we obtain the answer, we could return to our original time function. I advise to look, or in mathematical books, if you had this in some previous disciplines, in our university or on your previous education, or in internet, the most general idea. Wikipedia is not the best resource, but for the general overview, it is quite comfortable to look on. Generally, not so scientific resource, as it said, but the general review, it could be quite useful. We are speaking about operational calculus. The main idea is like this. Just you could, at comfortable time, look through, not to read everything from the beginning till the end, but look through the general idea, how to obtain from time function some operational function in variables instead of time, variables in terms p, some general parametrical function. And these transformations, these operational functions start from the mathematical Heaviside theory, and then was developed by Laplace mathematical theory, and the final view of such transformation is called Laplace transformation. Idea is like that. Instead of time function f from t, we, using some integral transformations, obtain some imagine of function in terms of some parametrical variable. We could write p, we could write s, depending on literature. It is the same idea. Instead of time function, after transformations, we could obtain parametrical function. And then the main difference, what type of time function do we have? Because if we have sinusoidal function, the transformation will be just concrete type. If we have not sinusoidal, any other time function, then this transformation will be different. If we are speaking about sinusoidal, the transformation will be in terms of complex numbers. The parametrical parameter, the parameter p will be j omega as frequency of oscillation, and j is imaginary value. In mathematical theory, mostly it pointed as I, but in electrical engineering, I we use as current. That is not to mix current and imaginary numbers, we use in terms j, just square root of -1, or the same as j square equals -1. Then for sinusoidal time function, we are obtaining some complex number, some complex variable. In terms that for example, instead of some current that has amplitude and initial angle, we are obtaining some complex vector, or in exponential form as effective value on the angle, or in algebraic form as a coordinates of this vector. And instead of a differential equation, for example, for coil, after transformations, we obtain algebraic equation for complex vectors in terms analogically to Ohm's law. Instead of some time dependence, if we had current, then after taking derivative, we will obtain some voltage. The voltage will be at least cosinusoidal function because we are taking derivative from sinus, and it will have a different initial angle. A little bit later, we could speak what will be difference between these angles. But in any case, it will be like this. And instead of such time function from t, we obtain some parametrical function from j omega after transformation. This approach gives us opportunity not to solve differential equations, but solve algebraic equations. And if we are speaking not generally from time function, but concrete about sinusoidal function, we could use such called Laplace transform and operate in complex numbers, and we could look how it is done, using generally this transformation is taking integral function in the way as you see here and here. Also, we could see some tables of characteristic, how it is done, what the main characteristic it has, also what could we find here interesting, also some basic table of the transformations. For example, instead of some time function, we could obtain some parametrical function, and so on and so on. Just propose to look at this mathematical paper from the beginning to the end, just to see the general idea. But we will use a little part of it, firstly on sinusoidal current, then for non-sinusoidal. Why I'm speaking such detail about it? Because starting solve sinusoidal current, a lot of people use two complex number and try to use these complex numbers in all tasks, independently of type of signal. For non-sinusoidal, for exponential, for any other type, and it reaches and them obtain lots of mistakes because of it. Because complex number, they are used only for sinusoidal function. It is type of transformation only for sinusoidal function. If we have not sinusoidal function, we also could use operational form of calculation, but we should identify which type of parameter we should use, because it depends from type of signal. For now, it will be j omega. Then, first of all, question about for you. Is it little bit
just a little bit understand.
Sorry, could you repeat?
It's complex, and I can't say I totally understand it.
Okay, did you see it earlier for some other disciplines? Did a teacher told something about it earlier?
Yeah, in probability, we can teach about Laplace function. And yes, maybe my senior high school, we have learned something about it.
Okay, perfect. Yes, I understand that it is could be technically not so easy and not so obviously, but the main idea to use some mathematical apparatus to simplify calculation. We are using some transforms. We have the view of these transforms, how to do them. It could be a little bit confusing or complex to did it on practice. For example, take some integral and obtain the answer. But generally, the idea, instead of something complex for calculation, obtain something simple for calculation. For example, for my students, I told some practical case, some analogy to see how it could be done. For example, One moment. Try to make some analogical from physics.
Okay.
Okay. Okay. For example, you are looking of, for example, you're making some physical experiment, and you want to identify the speed of moving some object into some medium, some general medium with some liquid, with viscosity and so on and so on. But you don't have measurement devices for measure speed. Generally don't have them near your hands. And directly speed you cannot measure. But for example, you have some other measurement device and could measure something else. For example, temperature. And if you could measure temperature of temperature difference of this medium, because of as speed is higher, generally because of resistance, the heating of this object should also increase. The temperature of this object, of this medium, should increase. And if you could measure the temperature difference after moving of this object, and if you will make some dependence between temperature and speed, between two different physics, you could find the answer. Because you have equipment for temperature, you are measuring temperature, after that obtaining speed, and as a result, you're obtaining speed. The idea of mathematical operational calculation, the same. If you cannot calculate something straightly, some time function, you try to calculate what you can. You are calculating function from some other parameter, from some parameter p, and after that obtain your final goal of your original function from time. That is the case, just as the mathematical apparatus to make complex calculation more simple. Instead of something you cannot calculate, or you could, but it is quite complex, calculate something more simple, using dependencies between these two functions or between these two equations. Something like that. It is okay in terms of general idea.
Is there have more examples?
I just want to say that it is not so important how we doing this transformation exactly. It's not so important what the view of this integral is, because it is just a technique how to do it. It is just a technical task. But the more just sorry, one moment.
Okay.
Yeah, sorry. Just I want to tell that most students, they are paying the main attention on the detail, that we have some integral, we are calculating this integral, and so on and so on. But they forgot the main idea, why are we doing it? Why are we using, what does what does transforms mean and why do we using them? Because it is just a tool. It is not a goal as itself to do it. It is just tool for obtaining the answer.
Okay, yeah, understand.
Okay. Just maybe to imagine some other example. Okay. Only try to find something very easy, not so mathematical or physical, to understand the main idea. Because this transformation, what do I mean that they are just tool? For example, some person want to build a house as the final goal. I mean, want to obtain some function, some equation for function. But if person cannot build this house, if he or she don't have necessary equipment, knowledge, and so on, he cannot build this house. But this person works on some work and reach money. For example, he or she is a programmer or IT person coding some system and reaching money. And after person obtain money, he could pay for other person to build house for him. The money is just a tool to reach the final goal. That is why if we cannot find initial function, we make some transformation for other type of function, which we could reach. For example, money is some tools to reach our final goal. And then we could transform this operational function into time function from our initial parameter. Then just a build house. That is why I'm telling that it is just a tool. And to reach this tool, we are making some transforms. But it is just an engineering task. It is just a technical details. But the main idea from one object, instead of one object, obtain other object, then to return to this one. Okay, let's see how we're doing it on practice, because I understand theoretically it could be not so obvious. Last time we speak that all our functions are sinusoids, and instead of this sinusoid, we want to obtain some some easier numbers for calculation. How we could obtain them? What does sinusoid mean? It is some function with period of oscillation, and this sinusoidal function could be obtained as a rotation on the circle. Last time I speak a little bit about electrical magnets, how they rotate, and making rotational magnetic field, and this magnetic field makes sinusoidal current as a result of rotation. Then, as sinusoidal movement, so sinusoidal oscillation could be obtained as a projection on the vertical x. If we will squeeze this sinusoid, we could represent it just as the moving through the vertical x through the vertical x. And any point from initial sinusoid, it could be obtained as a projection on the vertical x. Any point, as you see, after squeezing this sinusoid could be obtained as a projection on vertical x. Then, instead of sinusoidal oscillation, we could look on the rotation of some vector and dealing with coordinates on this vector on horizontal and vertical x. And these could be found after those Laplace transforms as we discussed. Instead of sinusoid, after Laplace transform, we could obtain some vector with initial angle, this vector. And then after moving time, when we're moving through this sinusoidal function through the time, it will be represented as rotation of this vector on the circle. Each period will be whole circle rotation in the coordinate system. About what vector we are discussing, what point of sinusoidal function we should take. We should take some average because in a different point of time, you will obtain quite different numbers that you have to find some average value for this sinusoid. What average value should be the most useful on practice? Some energetic characteristic. If we're speaking about power or energy, for direct current, we were speaking that we have some resistivity. On this resistivity, we consume joule heating on the constant power in watts. And if we will consume constant power for some period of time, we will take from the circle some energy in joules. Then, if we want to discuss some average value on the sinusoidal current, it is quite logical to take the energetic average. Some average value that gives us through the whole period of time, the same power that if we will multiply this power on the period of time, we will obtain the same energy as we get on direct current. And this average value is called effective or root mean square. And it is found, it could be found from this main restriction that power on DC that we have I square R should equals power on AC. To obtain it, we should integrate Joule heating of the sinusoidal current on the resistor, integrate on the whole period of time, and take the average value through this period of time. Here, there. These two powers should be equal. Because resistivity is the same on DC and AC, we could erase it, and I, some effective value, should be square root of this integral. And after substituting instead of current sinusoidal function, what it will be? It will be this function, this one, sinusoidal function, this one. After substituting, we obtain number 0.7, or in more precise numbers, square root of 2. From the amplitude value, if we have sinusoidal function from the amplitude current 10 amperes, then effective current value will be 10 divided on square root of 2. For example, when we speak in that using electricity 220 volts in our homes, that is mean that 220 volts effective value of sinusoidal voltage. On our house producing or transporting sinusoidal voltage, the amplitude value will be 220 on square root of 2. Square root of 2 times higher, but the effective some average value will be 220. It is the answer what length of vector are we taking. After representation sinusoidal function as vector, we are obtaining in terms of effective number some vector object. And after it, instead of all sinusoidal function, we will get a vector functions. And using all mathematical operations with complex numbers, all properties and characteristics, we are dealing with these objects. Using Laplace transforms, the integral function will be divide on j omega, derivative function will be multiply on j omega. And let's see some practical example to discuss all this theory. For example, let's assume that we have some sinusoidal voltage source as some electromotive force time dependent, and it operates on resistor, coil, and capacitor that are connected serial. Let it be 10 ohms of resistivity, frequency 50 hertz, 50 hertz, and let inductance will be, just one moment to calculate to obtain good numbers. Let the inductance will be 30 millihenry, resistivity like this, electromotive force will be sinusoidal, for example, 100 sinus omega t, where omega is an angular frequency depending as 2p from the general frequency. It means oscillation inside circle, where 2p is 360 degrees, or 2p radians, the whole circle. And our capacitor, let it be, for example, just one moment. Want to find good numbers for calculation. Then C 1 over 20, 1 over omega, 1 over 20. Yep. And multiply on. Let it be, for example, 3.2 millifarads. The numbers like this. What should we write to find the current? If we want to find current in this task, then we have to find general equations using the Kirchhoff's law. For such closed circle, we should write that electromotive force equals voltage of resistor plus voltage of coil plus voltage of capacitor. Substitute all that we have. It will be such sinusoidal function. If 50 Hertz frequency multiply on 6.28, 2p, 3.14 multiply on 2. And on 50, it will be 314. That we could say that it is 314 in radians on time, equals current on resistivity. Resistivity is 10 ohm. Voltage of coil, it will be L derivative of current. Then it is 0.03. And current derivative. And plus integral function of the capacitance, 1 over 3.2, 0.032, and multiply on the integral function. Integral function of the current per time. And we have to do something to solve this equation and to find current. As you see, it is quite complex task. That is why we are doing Laplace transforms to transform this, firstly, time function into the operational function, into the vectors, and then to throw away derivatives and integrals from our equations. How it will be look like? Instead of such sinusoid, we will obtain vector. This vector should be effective value 100 square root of 2 times less, square root of 2 times less, then in exponential form with angle. With here is without angle, that is mean this vector lies on the horizontal x, and it will be just J0, or other words, exponent function will be 1, equals 1. That is why we could erase it, and it will be only 100 divided on square root of 2. This equation is written on time 0. Then it equals I multiply on 10 plus. Also, according Laplace transforms, instead derivative we should obtain parameter p. This parameter p in complex numbers always will be j omega. Why it is so, I will will prove a little bit later, after 5 minutes. Then, instead of derivative, we should write j omega. It means j 314. Then it will be 0.03 j 314 and our current function plus 1 over 0.0032, and instead of integral, also from the Laplace transforms, instead of integral operation, we should write dividing on parameter p, 1 over p. It should be 1 for sinusoidal case, it should be 1 over j omega. Then here will be divide on j 314. And as you see, the second equation, the green one, is much easier for solve than the initial one, because it doesn't include differential, doesn't include integral function. It is just general algebraic equation. 0.03 multiply on 314, it will be 10, just equals 10. And 1 over 0.0032 multiply on 314, it will be 20. It will be just 20 over j. What does it mean, 20 over j? It is mean that we could multiply on j both parts. J square equals -1. And it's mean that we, instead of dividing on j, we could write multiplying on minus j. Just general algebraic equation. As you see, everything is quite simple. Then we could, and it is also include current, because here we have current. Then plus 10 and minus 20, it will be minus 10 instead all of these. And as you see, you have just ordinary complex equation J10. Then you could find current in complex numbers. Transforms 10 minus J10 into the exponential form. It will be, what does it mean? 10 minus J10. It is a coordinate of vector with hypotenuse 10 square root of 2 and angle 45 degrees, because both sides are equal. That is mean instead of this, we could write 10 square root of 2 in exponent form, j 45 degrees with sign minus because of minus here. Then square root of 2, it will be 2, it will be 20 here, and it will be 5 amperes. The answer is current that we are looking for. It is 5 amperes with angle 45 degrees plus 45 degrees in complex form. What does it mean when we return to original function? If we are returning at the beginning, it is mean that our current equals 5 square root of 2 from the effective value to the amplitude value. The oscillation is the same, 314 on time. And the initial angle is 45 degrees. That is how it is done. From the initial goal to find current and writing the equations and obtaining differential integral equation, using Laplace transforms, we obtaining complex numbers as algebraic equations. And for these complex numbers, we solving obtain vector, and this vector gives us some sinusoidal function here. It is the answer. And the main idea on the example. Please question if you want to add something.
No.
Okay. How it is clear for the first time? Is it okay or not exactly?
Not exactly.
Okay. We will practice a lot of tasks on it. How it is looks like on graph, on the physical graph. At the initial data, we have voltage that have amplitude 100 volts and 0 initial angle. The dependence of electromotive force. We want to find current, and as you see, straightly we cannot do it. Straightly it is quite hard task, and we don't know how to solve this equation. That is why we're using some Laplace transformations with concrete rules. We will write all these rules for all elements, and we'll use them just directly according to these rules. But after using them, we obtain a complex vector algebraic equation in terms of complex vectors. And the answer is 5 square root of 2 amperes with angle 45. It means that we obtain some current, with the value 5 square root of 2 amperes. And initial angle 45 degrees. Here is 90 degrees in opposite phase, and 45, it will be 1/8 of the period. If period of oscillation 360, then half of period will be 180, then quarter of period will be 90 degrees, and period over 8 will be 45 degrees. Here is this angle, 45 degrees. The graph of current. Graph of current. Could we find all voltages in this system? Yes, we could. We could use resistivities and find these voltages. In complex numbers, after we obtain vector of current, we could multiply it on resistivity and obtain vector of voltage for the resistor. If current is like here, then the voltage will be multiplied on 10, it will be 50 square root of 2 with the same angle. It is mean that for voltage of resistor, it will be the same graph with the same maximums and with amplitude value 50 square root of 2 and the same angle. What will be about coil? For coil, voltage is integral from current and in complex, is derivative from current, and in complex number, it is j omega L multiply on the current. As we calculate j omega equals 10, it is mean that we are multiply on 10, but angles move on, angle moves on 90 degrees, because j, if we have 1 here, j is a vertical x. And from 0 degrees, we obtain 90 degrees after multiplying on j. That is mean instead of 45, we will obtain 135. It will be 50 square root of 2, the same amplitude, but we should move this object on 90 degrees earlier than the green one, or on 135 earlier than black one, or 90 degrees earlier than green one. 90 degrees, it is a half of, it is a quarter of period, it is here, how it looks like. Then we could make the last operation with capacitor. For capacitor, we have integral. It will be minus j in complex numbers, 20 on current. It will be 100 square root of 2, but on the 90 degrees in opposite direction. It will be bigger amplitude, and moved not square period earlier, but square of period later here. And what do we see? That it isn't, that we cannot see nothing because of lots of graphs. Just one moment. Yeah, that is the general picture of all moments of time. As you see, it is quite complex and we cannot see nothing. It is very complex for our eyes, and it is very non-informal. Then, to make it more easy for use, we are taking some moment of time. Generally, it is taken 0 moment of time, this point. For this point, for each vector, we have some point, some concrete point. And we could represent all these points. Let's erase everything that we don't need because we have lots of old information. You have electromotive force with 0 angle, with length 100. Vector of electromotive force. Here it is. You have current vector with angle plus 45 as you calculate. What does it mean? It is mean that 0 point is 45 degrees moved from the 0 point of our coordinate x. Then you have a resistor vector. It is longer, not so long as electromotive force. Electromotive force is 100. Then long electromotive force. Voltage on resistor is smaller. Then you have voltage of coil with plus 135 degrees and length also 50 square root of 2. Square root of 2. It is here. Sorry, the same length. Then something like here. And on minus 45, plus 45 minus 90, minus 45. 0 point is here. Also, we are looking on 0 points all time. On minus 45, you have twice longer voltage of capacitor. Then representation of all points in 0 moment of time is here on vector form. If we will move the point of time later, we will obtain other points, and vectors will be the same oriented 1/1 between each other. The angles will be the same, but the whole picture will rotate on some point of time. For example, if we will move this picture onto quarter of period. Look on the black sinusoidal function. Quarter of period, then all this picture will move on 90 degrees. These vectors will be electromotive force. Let's draw it here. I think I'll just draw the second graph. Electromotive force will move on 90 degrees. Coil will move, current will move on 90 degrees on the starting point. The coil voltage and capacitor voltage will also move on 90 degrees. As you see, the drawing will be exactly the same, but with rotation on some angle. And you could obtain any moment of time by rotating your picture on the circle. And this is the idea, how to make dependence between sinusoidal function, because whole this picture is quite hard to understand for the vector form, because vector form for specific moment of time is much easier. The same, all these vectors you are drawing in effective values, it is mean that if it be a direct current, then for direct current, you should obtain these numbers. Instead of 100 volts of sinusoidal, you should obtain 100 over square root of 2 constant value. Instead of current, you should obtain 5 amperes current constant. Instead of coil volt, resistor voltage, you should obtain 50 voltage. Coil voltage and capacitor voltage will be neglected because they isn't influence on the direct current. For coil will be as a conductor with 0 voltage. The coil is orange, it should be 0. And capacitor where this capacitor, here it is. It should be with some value of voltage that we should calculate from the physical conditions of our circle. Why is it so? Because I think I just make it more complex for understanding. Because energetic characteristics, they are used only for resistor. We speaking about electromotive force and consumption of resistor. As electromagnetic field, in direct current, it will be different from alternating current. But the main idea, if we are looking on resistor, instead of sinusoidal function with different initial angle, on direct current, it will be straight lines in effective values that square root of 2 times smaller than sinusoidal one. And to obtain these effective values, we, in some moment of time, using vector form. It is our idea. Instead of all time moments, obtain the concrete one. Now, I also will show other example and the general approach, but for now, maybe you want to ask something or make something more clear. Please welcome, you can ask.
Okay, but everything is clear. Thank you.
Okay, okay, hope so. It will be fantastic. Then, what general laws, what general approach do we have? If we speak that every time, instead of sinusoidal function, we want to use complex number, then for all resistors, coils, and capacitor, or what was our colors, I think we write them yes. Instead of resistor, for the law U equals IR, we are using the same law in complex form. After Laplace transformation, this transformation is used in lots of situations. Also, as you said, in forgot English word. In probability theory, yeah, in probability. Also could be used in probability theory, in electrical engineering, and so on and so on. It was quite useful thing for represent differential equation in some algebraic equations in terms of operators. Then instead of resistor, we will obtain vector U and I that connect only through the constant, instead of differential dependence for coil, we will obtain algebraic equation. Instead of derivative, we will write J omega, multiply on the coil, and it will be current. And this thing is called reactive resistance. R is active resistance or ordinary resistance. J omega L is called reactive resistance and is pointed as X. But the variable also is in ohms. For capacitor, instead of equation 1/c integral of current, also we could write in complex vector, instead of integral, it is 1/j omega, and the same C capacitance on the vector current. And this value is also called reactive resistance of capacitor, and it is 0.1/omega c. Then, in all cases for capacitor, you are using this resistance. In all cases for coil, you are using this resistor, and the same Ohm law as for ordinary resistor. You see that in complex vectors, these equations could be represented as the same as Ohm law. Okay. Why is it so? I think I will prove next time, not to represent lots of information, because I think it will be worse for understanding. That is for now. For now, let's see like this. What does it mean? It means instead of electromotive force that we wrote, E from time, that it was 100 sinus 314t in previous task, we are writing just complex vector of electromotive force. And that's all, with zero angle. As we obtained previous, the current at the solution should be 5 amperes square root of 2. Yes, if I'm not mistaken. 100. I think yes. It was 5 square root of 2. (314t) with the same angle. With angle 45, minus 45 it was. As a solution of those tasks. But this solution we obtain as complex vector. The complex vector of current, the value 5 amperes, and angle minus 45 degrees. Just a complex representation. Using this current, we obtained voltage, that is time function. Current is also time function. Voltage is a time function, and we obtain it as 50 square root of 2 sinus 314t minus 45 degrees, and we also plot it on the graph. Then it means that we obtain voltage of resistor at the value of 50 volts effective value with initial angle also minus 45 in complex form. And so on and so on. For coil, the function was 50 square root of 2 sinus 314t minus 135 degrees. And it means that in complex form, we obtain such vector. And the last one for capacitor. For capacitor, voltage was in previous task 100 square root of 2 sinus 314 T plus 45 degrees. And the vector form was 100 E J45. What conclusion could we make? We could make the main conclusion that for all resistors, the resistance is R. For all coils, the resistors is J omega L. For all capacitors, the resistances are 1 over J omega C. All this value could be implemented only on sinusoidal current. It is the main restriction. Everything is only for sinusoidal current. And all coils moves all coils and all capacitors moves our current value on 90 degrees. One in one direction, other in other direction. Next time we will practice on some concrete tasks how to do it. But for now, just the main idea to remember it. To remember these three equations with resistances for coil and capacitors instead of three main differential equations. Then it was on time function. When we speak about time function, it is called to solve task in time domain. When we are using complex numbers, it is called to solve task in frequency domain. Generally, two main approaches: solve task in time domain and obtain original functions, or solve task in frequency domain and obtain their representations of functions. For now, I think that's all. For now, I think that's all. Let's briefly look on some examples on practice to see what I'm speaking about, and we'll discuss it next time more detail. Something like this. If you have some circle, instead of all element, you are putting resistivity, three type of resistivity or conductivity in complex numbers, and you could substitute, you could compare current and voltages using terms resistivities or conductivities. Make equation and obtain solution. I want to find some practical example just to show what I'm speaking about. Just a moment. And it will be all for today. Some task. Here it is. 3.16. For some elements, you are using resistivities in complex form and doing exactly the same that you did on direct current, calculating series connection, parallel connection, then also serial connection, but in terms of complex numbers. Obtain complex vectors, and it will be the final answer that you could transform into sinusoids using Laplace transformations. But you shouldn't do this transformation just in general form using integral functions, but you already have the tables of the final results, because these transformations is already known for all electrical engineering functions. That is why you are just using complex numbers, generally the same as in direct current, and from these complex vectors, you could obtain sinusoidal function, as I showed previously. Something like that. Next time, we will practice on these tasks using complex resistors, as I show on previous picture. You could look through this video once more to write this on some paper, just to look on it every time for solving tasks. Resistivity R, for coil J omega L, for capacitor 1 over J omega C. Complex resistivities. That's all. For now, that's all. Please, questions.
No question. It's clear. Thank you.
Okay, welcome. Thank you too. Then today's lecture was lots of materials and I think quite hard, but next time will be mostly practice, and I think it will be a little bit shorter and little bit easier. Then thank you for your attention. We wish you a nice day. See you next time. And
okay, thank you. Have
goodbye.
a nice day too. Bye.
Thank you. Goodbye.